All righty, folks. How y'all doing? Yeah, it's good to see you guys again. Well, today we're going to deal with some theory, a little bit of theory. And the idea behind this is we're going to build up where we're going with integration, but we've got to kind of take a step back. And we got to now look at how to find area, namely how to find area under a curve. And for us, the main way we're going to do that is using rectangles. So for instance, if I take a look at this curve right here, there is no rectangle that I can draw that will allow me to get this area perfectly. It's just not going to happen. I mean, I don't care how many rectangles I draw. I can't draw personally enough rectangles to get this area correct. So we're going to have to look at it as some way and somehow we can somehow create that area model. So let's take a look at this. If I want to find the area underneath these endpoints, and you guys have these in your printed notes, so you can access them if you want to. But notice there's endpoints on this closed interval that I'm looking at. And this distance, this rectangle I'm going to try to create, remember that a rectangle is always going to be some base times height. Now, what if I were to say I want to use a single rectangle to try to figure this thing out? A single rectangle. And if I try to use that single rectangle, move this up just a little bit. If I try to use a single rectangle to determine the height or determine the area underneath this curve, it's not going to go well. And I think we can all kind of say that. So I have some point here. The base of my curve, the base of my rectangle is going to be between these endpoints. So the base of my rectangle is going to be between these values right here. It's between my two x values. And we can just go ahead and call that, we're calling them B and A here. So the base of my rectangle is going to be sum B minus A. It's sum B minus A. So that's my width. No matter what my area is, the base is going to be sum B minus A value. It's the height that can change. And if you look at it, on this one right here, I'm using the left endpoint. So we call this a left sum because I'm using the left endpoint to figure that out. So that means my height then, if I draw this in here, my height is going to be located wherever that value is. Now, that height is not very long, is not going to be very tall. If you notice, here's the f of a value. That's the y value. So that means the height of this thing is f of a. So this height would be f of a. This one right here is called a right sum because you're using the right endpoint value to determine the height. So in this case, I come over here to the right endpoint value and I go up until I reach that right sum. Now notice where the left sum up here really drastically underestimated the area. This right sum was really way, way, way too big times f of b. It's way too big. So that means the area is going to be lying somewhere between that left sum and that right sum. We don't know where, we don't know what it is, but it's somewhere between that left sum and that right sum. Now, what some people like to do is they like to think of B in terms of the starting point, where it starts at A, and then I'm adding whatever the base of my rectangle is. So adding that B minus A. Basically the difference in them. And so that's another way you could actually see this area. This area can also be looked at as our width of our rectangle times, instead of B, some people like to think of it in terms of the starting value. So A plus whatever that width would be. And some of you are probably going, what's the point of that? Well, we're going to build on this idea here in a second. But notice all we're using here is some length and width, some base and height to try to figure out what the area is underneath that curve. Well, that's not going to really give me an accurate view of what it is. So if I wanted to get a closer view, I'd have to create more rectangles. So let's create more rectangles. We just did that. Let's create more rectangles. What if I let one rectangle be here, to the halfway point, and the other rectangle would be here, the other halfway point. Let's make that a little darker so we can see it a little bit better, huh? So here's my first rectangle. And then I take it, that gets me to the halfway point, or when B minus A is divided by 2. And my second rectangle. Notice, that's a little bit closer. This is a little bit closer to a decent looking curve. I mean, it's not perfect by any stretch of the imagination, but it's closer. So if we had B minus A all the way across, well, now we're not B minus A. We said we were going to only go half the width. So this is B minus A over 2. This width is also B minus A over 2. We only went half the width. So if this one was at F of A, so that height is F of A. And then this height, this X value, notice what it would be here. This X value right here is this A plus whatever that half a width is. So when we plug that in there, we started A and we went 1/2 a width over. So that meant that this height was F of A plus B minus A over 2. And we could figure out what this area is. And if you notice, that's what they have going on here. They took the width and multiplied it by the height. That's what this was. And then they did the next one. They took the width, still B minus A over 2, but they multiplied it by the height of it. And that was this rectangle right here. So that's what they're doing. They're basically taking these rectangles and they're figuring them out. Well, what if they decided to do, instead of a left sum, they decided to do a right sum? And look what those rectangles would be. So notice the green rectangle essentially became the purple rectangle. And then the green rectangle here. Now it's still an overestimate, but it's getting to be closer. So now they're not starting with the left values like we did over here. Over here, we use the left values. Now we're using the right x value. So we're using this one and we're using this one. We did 1b minus a over 2 over to get the purple one, and 2b minus a 2 overs to get the second one. So again, the width is still, for each of these, b minus a over 2. But they're using the right value instead of the left value. So that means this is f of a plus, I should use a bracket on that. B minus a over 2. And this would be f of, and so for the most part, guys, I just kind of want you guys looking at what's going on here. We just need to have an understanding of kind of the notation of what's going on here. We don't necessarily need to know it perfectly 100%, but we need to know the notation. And we can use this now and write this, and again, you'll see, here's the purple arrow over here. So this rectangle, we got it right here. You can notice how this purple area and the green area, these are essentially the same values. Notice how those are the same areas? Because it was the same endpoint. Because what was the left endpoint for the green rectangle here is the right endpoint for the purple rectangle. And then we have our green area. If you take the area of that one, it'll be right about here. You can kind of see that right there. But one of the things we can do with this now is we can start to write this in as a summation and sigma form. Each one of these is some b minus a over 2. So if we take a look here, say we start at 1. Notice we only have 2 rectangles. So I'm going to let it go to 2. The width on all of them is some b minus a over 2. And I'm multiplying it by some f of a plus some b minus a over 2. Now, the thing to remember here for the index of this, when we're trying to write this, is we had how many b minus a's over 2's altogether? On the second one, notice we have 1 b minus a over 2. But on this one right here, notice there's no b minus a over 2's. There's none. So there are 0 b minus a's over 2. I'm going to erase that because technically we don't really want that there. There are 0 b minus a over 2's. So I'm going to use this idea of our index to turn this into just an f of a. I'm going to always subtract 1 from my index. So this says, if I plug 1 in here, I get 1 minus 1 is 0. There are 0 b minus a over 2's. So really what this is just this f of a. If I plug 2 in here to get my second rectangle, remember the index just means which rectangle you're dealing with. And again, let me write that here. All this index is just which rectangle. Just which rectangle you're dealing with. So when I is 1, that means I'm dealing with the first rectangle, the purple one. When I is 2, I'm counting from 1 up to whatever this top number is, 2, that's the green rectangle. So 2 minus 1, that's 1. That means I'm have 1 b minus a over 2 partitions heading over. And we can do the same idea over here with our right sum. Notice, for the right sum, they both have b minus a over 2 as the width. And the height, they both start off with a, but I'm using the right value. So how many b minus a partitions did I have to go to the right? Well, on the purple rectangle, I had to go over 1 partition. And on this one, I had to go over 2 partitions. Well, that is this actual number. So in this case, we're going to just have our partition be the letter I. So how many b minus a over 2's did we go? Well, we went over I. So remember, I is just how many, we call them partitions, but how many rectangles are partitions we went over. So that was I. Notice that's the only difference between a left sum and a right sum. Is just the left sum has the index -1 because you're always one less partition, where I is the right sum. So we got all kinds of things going on here, right? All kinds of things. So we're just doing a little theory, like I said, again. And then we'll see how all the theory kind of ties itself together. So let's keep going on our little picture here. What if we keep going? And we add more partitions. More partitions. So now, let's take a look at what we have here. We had a purple partition. We had a green partition. We've added more. And now we have a red partition and a blue partition. And notice, the more partitions we use, the closer our area gets. But what are the A values you're using? Well, you're using however many partitions over. So that, notice, on the purple, we had 0 partitions. It was just A. On the green, we went 1 partition over. So that's why we have the 1 right here. On the red, we had to count over 2 partitions, which is why we had 2 partitions. Remember, it's always the third rectangle went over 2 partitions. The green rectangle, or number of widths. So the purple, the first rectangle went over 0 widths. The second rectangle, the green one, went over 1 width. The third rectangle, the third area, only went over 2 widths. And the fourth area went over 3 widths. So however many widths we have, we only went over 1 less than that. So notice, our right sum, this formula is still the same. It's just now, instead of dividing by 2, what are we dividing by? Well, we had 4 rectangles, so we're dividing by 4. However many rectangles we have, that's how many we divide by. So this time I had 4 rectangles. My width was b minus a over 4, and I changed it. So that means potentially I'm dealing with the same thing here with the right sum. Okay, so this was, again, was my left sum. And I'm thinking the right sum is going to be something kind of like this now. So what if I add more partitions to my right sum? I ran out of room there, didn't I? Yes, I did. All right, well, let's see if I can't actually write it up here then. Let me rewrite that real quick. My right sum. This is what we had. And we had an orange rectangle around the index to let us know how many rectangles we went over. All right, so how does this work then for the right sum? So let's draw our rectangles so we can see them a little bit better. Okay, so this time we're using the right endpoint, not the left endpoint. We're using the right endpoint. So there's our first one. So we're using the left values. There's the second one. Here's the third one. And here's the fourth one. And notice, look at what the purple one's using. It's using the right endpoint. So it went over one rectangle. Went over one width. The green one is using this one because it went over two rectangles. You guys see the rectangles there? Went over one rectangle for purple, went over two widths. One width for purple, two widths for green. What about the red? It went over three widths. So it had a 3. For blue, it went over four widths. So it was a 4. But notice, the only thing that would have changed with that one, because we're doing the same thing, the only thing that changed is, again, we don't have two widths, now we have four widths. I just noticed I had an in there. That's coming up here in a second. And when we went from four widths, now we are even closer to having the exact area. And friends, that's what we see down here. So when you get to these things, that's what we see down here. We're just adding more rectangles. The I just tells you which rectangle we're dealing with. I just tells you which rectangle we're dealing with. So how many widths we're going. But realize all of this fancy schmancy thing here represents is some base of a rectangle and a height of a rectangle. It's just base times height. They're just a series of rectangles. And we have this summation form to be able to write it in. Again, so we're doing a little bit of theory here today. So that's our base. And this would be our height. So the more rectangles we add, the better and more exact our answer is. So eventually we get to the point where we say, okay, well, what if we had 8 rectangles? It'd be closer. And then you say, all right, well, what if we added 800 rectangles? That would be a lot closer. And we just keep getting closer and closer and closer. So then we get to a point where we say, okay, well, what if we allowed the number of rectangles in theory be infinite. And if they were infinite, we would have the exact area underneath that curve. The exact area. And so it ends up turning into something that looks like this, where n is the number of partitions, or partition is just another name for fancy name for rectangle. And we say, okay, we can just keep increasing this n value to create more and more and more rectangles. And eventually you say, okay, well, what if we allowed n to become infinity? Notice nothing changed here. We still have our base. There's our base. And we still have our height. So we're just taking, in theory, an infinite number of rectangles. Base times height, and we're going to have an infinite number. Base times height, and we're going to have an infinite number of rectangles. Well, eventually, here's what mathematicians started saying. They said, well, wait a second. We can probably clean this up just a little bit more, because if we remember that delta x, or the change in x, is the difference in x, that really is the same thing as b minus a. So they added one thing. Instead of having this be b minus a, they said, well, what if we let this difference in x, the width, be b minus a divided by n? And when they did that, here's what happened. This right here became delta x, the width of my rectangle. And this right here became delta x, where it's assumed that delta x is b minus a over n. Notice the a value is still there, right? That's still our starting value. That never went away. But we can just rewrite it a little bit cleaner. So there's a little bit less going on. And again, nothing changed, right? This is still nothing more than the base of a rectangle times the height of a rectangle. We have an infinite number of rectangles. And likewise, we can have the same thing over here as well. Area, oops. The area of this, as we go out to an infinite number, you guys are doing really well with this. I appreciate it, because this is really our big giant theory day as we're kind of setting things up for the remainder of the semester. Times f of a plus delta x times I. And again, this is just a fancy schmancy way to say we have an infinite number of rectangles, base times height. That's all that says. Infinite number of rectangles, base times height. The base is always the difference between the values, and the height is whatever you do when you plug it into the y value. So that's where we end up something looking like this, which is what we just did. So what are we going to do with this stuff? Let's say I give you a function like, oh, write the left sum for f of x equals the square root of x from 1 to 4. So how's this going to work? Let's not use left. Let's use right, actually. All right. So first up, let's figure out what our width is. So delta x, that's our a minus or b minus a. So 4 minus 1. And we're going to have an infinite number of them. So that's our delta x. So as we put them all in here, we have our delta x. So 4 minus 1n. Times f of a. And our a value is the very first one. So there's our a. So f of 1 plus delta x over n. So now let's just go ahead and get rid of delta x here. We don't need delta x anymore. Let's just go ahead and call it 3 over n, because that's what it would be in this problem. b minus a, that's 3 divided by n, plus our a value, 1, plus 3 over n, that's our delta x, I. And if we go one step further and we plug it all in, so all you guys really need to have to do with this stuff, as far as the theory, is you need to be able to recognize what the width is and what the height is. So now in place of f, I'm going to go ahead and plug in my function. And if you notice, this right here is where my f of x is. So wherever I see my x, I'm going to plug that in. So f of 1 plus 3i over n. So that would be the summation form, the right sum form for this value. Let's have you guys try one yourselves. Write the left sum form. The left sum for f of x equals, let's go x cubed from, let's go 2 to 6. All right, friends. So here's what I want you guys to do. I want you to go ahead and pause the video and see if you guys can actually go through and write the left summation for that value. All right, friends, let's see how you did, right? So we have a delta x. That's going to be our b minus a. So 6 minus 2 divided by n. So that'd be 4 over n. Okay, here's my a value right here. So we plug it all in to infinity of n I equals 1. My width, 4 over n, times my f of x. So whatever it is, cubed. So now we got to just plug our values in here. So we're going to have our a, our initial value, plus our width, 4 over n, times I minus 1. And we're done. That would be the left sum for this function. Well, friends, that's all fun and good, but what do you really, the question you probably are asking is, what do you really need to know? What do you really need to know for the AP test? So you'll see those summation forms. For the most part, it's not every year you'll see one, but you'll see one every once in a while on a multiple choice test. Here's what you guys need to be able to do. Given a table of values, so we don't necessarily need to know what the graph looks like. Say we actually had a graph of it. And I asked you to figure out what would be the left sum and the right sum of this function. Could you do it? Now I'm going to graph an idea of what it looks like, just so you can see. Realize it's probably curved, right? It's probably curved. And this is just a guesstimate of what it looks like. You don't need to graph it ever, but I want you guys to kind of just see what it looks like. Oops, I went the wrong way. I need to make these a little bit bigger. But we need to be able to figure out the left sum and the right sum. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this represents some function, and I don't know every value on the function. I just know a few of the values. I know I have 0, 3. I know I have 2, 4. 3, 7. I have 5, 6. 7, 7. And I have 10, 10. So if I asked you to find the left sum, notice what's going on here. I'm asking you to essentially figure out what's this value, what is this value, and you'd be doing a whole bunch of areas. And again, I didn't necessarily draw this terribly well. Be about there, there. Something like that. I'm asking you for the area of these values. Well, here's how we end up doing this. So we don't go too terribly crazy. We just kind of look at the width. Notice the width here on this one was 2, 1, 2, 2, and 3. That's just the difference in the x values. And then the y values are really whatever the left endpoint is. So the first one is 3, 4, 7, 6, and 7. Those are our y values. So if I wanted to find the left sum, I don't have to draw out the whole thing. I just need to find the difference between them. And then do 2 times the first y value, so 2 times 3. 1 times the second y value. 2 times the third y value. 2 times the fourth y value. And 3 times the fifth y value. And that would be my left sum. All right, Fred. Oopsies, didn't want to do that. Why don't you guys do me a favor now? Why don't you guys see if you can figure out what the right sum would be using this idea. What would be the right sum? Go and pause the video and take a gander at it. All right, so let's see how you did. First of all, I'm going to draw again just because I want you to see it. I want you to make sure that you kind of really have a good grasp of what's going on here. So now if I'm using the right sum, realize I'm now going to the right value. I'm not using the left value. I'm going to the right value now. I'm going to the right value. I'm going to the right value. I'm going to the right value. And I'm going to the right value. Totally missed that one, didn't I? That's what you get for doing it. So I'm looking for these rectangles. Notice the widths of them didn't change. The only thing that changes is I'm using now the right value. So instead of using 2 times 3, 2 is going to get paired with 4. Be 2 times 4. And again, I would expect you guys to be able to go ahead and figure out what all these are on your calculator. You just plug them in. 1 times 7, 2 times 6. Oh, let's try 2 times 7 and then 3 times 10. Notice we used all the numbers on the right. So 1 times 7, 2 times 6, 2 times 7, and 3 times 10. And this is essentially how you would do a Riemann sum. You just grab your values in the table and you would deal with it that way. Let's have you guys try one just for the fun of it. Oh, let's see. I'll give you a 2, 4, 5, 8, 11, 12, 17. And let's try this. F of x. 1, 3, 5, 4, 2, 5, 8. All right, friends. Why don't you guys go ahead and pause the video and find the left and right sum. Just write an expression for the left and right sum for whatever graph would have these values. All right, let's see how you did. First up, you got to know your widths. You got to know what the widths are. So we just subtract them. 2, 1, 3, 3, 1, and 5. All right, so if I'm using the left values, it's going to be 2 times 1, 1 times 4, 3 times 5, 3 times 4, 1 times 2, and 5 times 5. So it would look like this. And again, I'm not going to multiply them all the way out. I'd let you guys do that one. So 2 times 1, 1 times 4, 3 times 5, 3 times 4, 1 times 2, and 5 times 5. And if I'm doing the right sum, it'd be 2 times 4, 1 times 5, 3 times 4, 3 times 2, 1 times 5, and 5 times 8. It would look like this. Two times 4, 1 times 5, 3 times 4, 3 times 2, 1 times 5, and 5 times 8. Adding up a whole bunch of areas, base times height. That's kind of an ugly 8, wasn't it? I bet I can fix that. 5 times 8. All right, we're going to try one more, and then we're going to call it a day, friends. One more, and then we'll call it a day. And then after that, I'll see you guys on Monday. All right. Now, first thing I want you to do is I want you to go through and find the left and the right Riemann sum for this problem. Go ahead and hit pause, and then I'll do it as well, and then we'll look at our final thing. All right, here we go. Left and right Riemann sum. So first up, width is 4, 4, 4, 4, 4, and 4. Notice, all the widths were the same, so we say that is normed width. Normed width is when all the widths are the exact same. Partitions or rectangles are the same value. So this is normed width because all the width or of the partitions or rectangles, they're the same value. So it's the norm thing. So left sum, again, deals with all the left values, 3, 5, 6, 7, 5, and 8. So the left sum, 4 times 3, plus 4 times 5, 4 times 6, 4 times 7, 4 times 5, and 4 times 8. And then we have our right sums, 1, 2, 3, 4, 5, and 6. Four times 5, 4 times 6, 4 times 7, 4 times 5, 4 times 8, and 4 times 9. I need to rewrite that 6 there. That's a little sloppy. So now we can do a left sum and a right sum no matter how many partitions we have. But the last sum we're going to look at today is a midpoint sum. Two things have to exist on a midpoint sum. First of all, we have to have an even number of partitions. And every partition must be norm width. So in this case, notice I have 6 partitions. There were 6 fours there, and they were all the same width. Because of this, I can do something called a midpoint sum. And here's how a midpoint sum works. What ends up happening is, first of all, to find the width of a midpoint sum, we have to create a midpoint. So in order to do that, I have to skip a number. So on a midpoint sum, my width would be 8. To find the midpoint sum, I would skip a number. So notice, however many sums I have, my midpoint sum, or how many rectangles or partitions I have, the midpoint sum will have half of them. So for my midpoint sum here, I have 3 partitions instead of 6. So what value am I going to use? What y value am I going to use? Well, let's take a look at this. So for this first partition, this right here would have been my left sum. For this one, this would have been my right sum because it was on the far right. And by skipping one, we created a number in the middle that would have been my middle partition. So this right here ends up becoming my midpoint sum, my mid-value sum that I would use. So by skipping a value, I created a way for me to have a midpoint sum. So let's look at the next partition. Why don't you pause the video here and see if you can figure out what would be the y value for the next partition. All right, let's see how you did. So here's my left sum for the second partition. Here's my right sum for the second partition. So the midpoint sum would be the number in the middle. And one more time. Here's my left sum for this last partition. Here's my right sum for the last partition. So therefore, the midpoint sum would be the number in the middle. You can see why midpoint sums, you have to have very specific things. They all got to be, you have to have an even number of partitions you're dealing with, and they have to be normed with. All right, friends. So we talked about the theory behind Riemann sums and area in general, area under a curve. And then we looked at some of these Riemann sums, how they might apply on tables. So I will see you guys on Monday when we get back from the weekend. Take care.